So the lab tonight is actually something we probably should have done either week one or week two, because it is really important for scientists, for technicians, for pretty much anybody who works in a field where you need to measure things and you need to give out doses of things. You need to be able to know what your uncertainty is. I mean, we treat uncertainty like it's something that we're never going to know anything about because the word uncertain is right in it. But actually, we can do a pretty good job of discerning how much uncertainty we can expect in a particular measurement. And, like in a clinical setting, how important that would be, giving doses of highly dangerous drugs or radiation or anything like that. Not only do we need to give the correct dose, but we really need to have an idea of what the uncertainty is. Because if you're dealing with something like really toxic, an error or an uncertainty of plus or minus, let's say 25%, isn't going to cut it. Because you may wind up giving a lethal dose to somebody, even though the measurement you took on it falls within, plus or minus 25%. So tonight we're going to figure out, how do you do that? How do you figure out what the uncertainty in your measurements are? And what can we do to make them as small as possible? We're never going to eliminate them. Basically, it's impossible to have any measurement be exact. That just doesn't happen because we all use instruments. Instruments are only good up to they're only rated to a certain precision. And then you have us weaklings with our failing eyesight, whatever else, also being a part of taking measurements. So how are we going to deal with the situation? So we're going to use sort of just basic measuring equipment that we've been given for home labs and determine what kind of accuracy and what kind of uncertainty will be associated with using that particular glassware. And the glassware we're going to be using, some of them are designed for measurements and some of them aren't. And it should be fairly obvious by the end of the lab which ones are good for measuring and which ones aren't. So we take measurements for every single lab, right? I mean, it's basically an exercise in measurement. You have a hypothesis, you think this is what's going to happen during an experiment. And then the only way you're going to actually validate your hypothesis is if you do the measurements afterwards and see if they agree with your idea. So we're going to, we measure length, we measure weight, mass, volume, temperature, pressure. There's all sorts of things that we would measure. And in this particular lab, we're going to focus on two. So we're going to focus on how to measure mass and how to measure volume, and looking at common equipment used for both and getting an idea of what's the uncertainty of measuring mass and volume. So this is what we sort of typically think about when we're measuring volume. It's sort of pictured at a 10 mil graduated cylinder. And you can see from here, we know that the volume of water, blue liquid, or whatever it is greater than 6 mils, but it's less than 7. And then if we look at the tick marks in between, we can go even closer. We can get even more precise in our answer. We can see that it's greater than 6.5, it's greater than 6.6, it's greater than 6.7. So I can say it's greater than 6.7 mils, and I can say that it's less than 6.8 mils. But that's really about as precise as I can get with this particular instrument. And then I have to make a judgment call, looking with my eyes as where the meniscus falls in between 6.7 and 6.8. That'll give you an idea of the sort of uncertainty you would expect with individual pieces of equipment. So remember, there is a difference, a big difference. And you notice this in your pre-lab. There's a big difference between accuracy, which is how close you get to the same, how close you get to the correct, so-called correct answer. So if you're weighing something or taking the mass of something that a very, very accurate measurement beforehand said is 12.5689 grams, for instance. Now you were using one of our scales that doesn't have that kind of accuracy. It's good up to, like, 2 digits past the decimal, but certainly not 4. So if you were to measure it and get 12.57 grams, that would be extremely accurate, right? If you were to measure 12.52 grams, that'd be less accurate. And if you got 12.04 grams, that would be really, really inaccurate. Now, related to accuracy, but not quite the same thing, is the precision of an instrument. Now, the precision of an instrument or a measurement basically tells you how good that instrument is at giving you the same answer every time. Now, we think of that as generally, that's a good thing, right? Yes, it is a good thing. You want to have a precise instrument. But if, for instance, I was to measure this mass with a very precise instrument, and I got 12.5599, and then 12.5598, and then 12.5597. Those are very precise numbers because they're very reproducible. They all look the same, right? Meaning I have a very precise instrument. It's precise down to like 4 digits, but it's not accurate because I'm not getting this answer. So that's the difference. And ideally, we'd like to have both. We would like to use a precise instrument and use it accurately. So the sort of errors that crop up when we're taking measurements are systematic errors. Systematic errors are generally ones that it's basically our fault. Because we're using an instrument and we're not using it correctly. And the example that's given in the pre-lab here is having an alarm clock that's slow by 5 minutes. So it's slow by 5 minutes, and it's the same 5 minutes every day. It's always 5 minutes slow. And so what you would do to correct that particular error is to set it properly. But sometimes just go, I know it's 5 minutes slow. It's fine. So you have an error, you're living with it. But if it's some sort of systematic error in measurement, that's more important than just like making sure you wake up at 5 minutes earlier than you're supposed to, or 5 minutes later. It's something more important than that. You have to fix that systemic error. So that's the sort of error where it's the same every single time, and it's either positive or negative. So it's either slower or faster. It's bigger or it's smaller. It's has a greater mass or it's a lesser mass, and it's always the same. So that's a systematic error. Relative errors are ones that are either positive or negative. And that would just be related to just sort of scatter in the data. for instance, if you took a plot of, let's say, 100 different cars, all going 60 miles an hour, and you looked at what their speedometer actually said, you get something that looked like this. There'd be some that'd be right on 60. There'd be some that's a little bit above 60, but some a little bit below 60. And so most automobile manufacturers have a tolerance of like plus or minus 2%. So that's pretty close, right? So it means that if you're driving at 60 and your speedometer says 61, that's close enough generally. It's not going to get you out of a speeding ticket if you say, well, you know, I have a plus or minus 2% error. That doesn't get you out of a speeding ticket when you're doing 120 in a 70 zone. So that is an acceptable, we say that's an acceptable level of error, and we express it as a percentage. So that's something you'll be doing tonight, because the absolute error in measuring something in a 50 mil cylinder is always going to be more than the absolute error measured in a 10, because you're measuring larger volumes. Now, the relative error may be the same. So that's why we need to look at the relative error. We're dealing with imprecision in measurements. So we express that as a percent error. Can anyone tell me what these lines mean? When it has these lines between like measurements minus actual value, and then has these two lines on either side. What do those lines mean?
It's always absolute value or always positive.
That's right, exactly. Excellent. Yeah. When we're talking about relative error, that's the very first part of the lab tonight, is measuring the mass of two different cups that should be the same, pretty much should be exactly the same as each other. They were manufactured at the same time in the same plant with the same equipment, using the same tools and the same supplies and everything else. They should be pretty close to each other. So if, for instance, somebody working for Subaru was like, testing their speedometers and noticed that, some of their errors were above and some were below, and didn't convert to absolute value, you might get a relative error of 0. If half of them were above the line and half of them were below the line, they would cancel each other out. And so you could have like huge errors, but as long as they were errors going faster and errors going slower, they'd cancel each other out. So we always present errors with an absolute value, because it doesn't matter whether they're greater or lesser. What really matters is how different is it from the actual answer. Will tell us how precise and how accurate our measurements are. So random error, I mean, that's where we come in. Random error is just really not something we can do much about. We can, like it says here, we can get better at designing experiments and get better. We work longer in the lab. I mean, someone who's been working in the lab for 20 years is going to do a better job at reducing the error in their measurements than someone who just started last Wednesday. So, but you can never eliminate it completely, because there's always going to be judgment, especially when we're using measurements like this. We're always going to have some amount of random error, because no one is going to be perfect at figuring out, if this is my meniscus in the graduated cylinder, no one's going to be perfect at figuring out what it is every single time. Sometimes we're going to think we're looking at it exactly on the level, but we're not. We may be a little bit below, we may be a little bit above. Practice with doing these sort of things will shrink that amount of error, but it'll never go to 0. So there's always going to be some uncertainty. And that's the limit of quantifiable measurement with confidence. Confidence meaning if I get a measure of 12.01 grams, I know that that is plus or minus 0.01 grams. That is knowing what your uncertainty is and having confidence that that's either 12.01, 12.00, or 11.99. And I can live with that. That's the amount of error I am certainly comfortable with. Now, if it was 12.01 grams plus or minus a gram, well, that makes these numbers pretty much useless, right? Because that tells me it's either 11 grams, 12 grams, or 13 grams. It's somewhere in there. And that's not good enough. So we need to be able to figure out what our uncertainty is in measuring mass and our uncertainty in measuring volume. So one of the things we're going to learn about is figuring out what intervals are. Now, intervals are basically what you have the greatest confidence in measuring this volume. So this is just blowing up the meniscus from the previous example. So you can see again that it's somewhere between 6.7 and 6.8 mils. And then depending on who it is that's reading it, some people are going to say it's 6.75. Actually would think it's a little bit less than that. To me, that looks more like 6.73 maybe. And somebody else would say, no, that looks more like 6.74. And someone else said it's a 6.79. But the one thing we can agree on is that it's somewhere between 6.7 and 6.8. We know that for absolute certain because we know we can see it's higher than 6.7. It's not on the 6.7 and it's below the 6.8 because that is what our intervals are on the piece of equipment we're using. This particular graduated cylinder has ticks at every 0.1 mils. And so we'd say that our high interval is 6.8. We know that it's less than 6.8. That is the highest it could be. We know it's not 6.7. It's between 6.8 and 6.7. So the low interval would be whatever is written on the particular piece of equipment we're using that's less than where we see the meniscus. So the measured value is basically somewhere in between the high interval and the low interval divided by 2. And that basically tells us what our uncertainty is in that particular measurement. So we would say that the measurement here is whatever you said it was, 6.75, 6.74, 6.76, plus or minus 0.05 ml. So that's the uncertainty expected for that particular measurement. Now, if that isn't accurate enough, then you would use a different piece of equipment. Maybe you would measure the mass of the liquid rather than its volume, which is something we're actually going to do tonight, because we know we can measure the mass more accurately than we can measure the volume, because we have our scales. We don't have to rely on our judgment in looking at the meniscus. We can just, if we use it properly, we should get more accuracy than that. And that is actually how we're going to be checking our work tonight. So these are the materials we're going to need. You're going to need a thermometer. You may ask yourself, why do you need a thermometer? But of course, you're not asking yourself that because you read the instructions already. So we're going to be using, obviously, oops, let me go back. We're going to be using our scale to measure masses. And then we're going to be using 4 different things. different things to measure volume. A 10 mil graduated cylinder, a 50 mil graduated cylinder, a 25 mil flask, and a 250 mil beaker. And you're also going to need 2 plastic cups that are the same. Anyone tell me what we need the thermometer for? Why do we need a thermometer for this experiment? We're measuring volume, not temperature, right? So what's with the thermometer?
Check the temperature of the water.
Why do we need to know that? That's right, but why do we need to know the temperature of the water?
To verify the density.
That's right. We need to know what the. So why is the density going to help us in this particular experiment? You're absolutely right. We need to know what the density of the water is. Well, how's that going to help us? What's that going to do for us?
Since we're getting the mass, then we have the density, we can get the volume.
Genius. Yes, exactly. So we're going to measure the volume, using our eyes and everything else in each one of these different pieces of glassware or plasticware, if you will. And then to check on whether how accurate we got it, how precise, basically how accurate our answer is, we're then going to take the mass of the water. And we pretty much know that like the density of water is dependent on the temperature. Like the hotter it gets, the more and more the molecules start moving around. They start moving a little further apart from each other. The molecules start getting a little further apart, and that makes the density go down. So we're going to check. We're going to get the mass of the water, and then we're going to convert it into a volume, and then see how close we got to, like for instance, we're supposed to measure 7 mils of water in the 10 mil cylinder. Now, if we get a mass of 6.98 grams, we pretty much know that's really close to 7 because the density is around 1 gram per ml, right? But if we were to get something like 5.92 grams, that wouldn't be too accurate. And the density is going to be dependent on whatever is the water you're using. So the water you're using should be at room temperature. If it's not, sort of measure the temperature of the water directly. You don't want to use cold water and you don't want to use hot water. You want to use water around 20 degrees or so for this particular experiment. Oops. So the very first thing we're going to do is figure out what the uncertainty is in the balance. So with the balance, we're just going to take 2 cups. Label them 1 and 2, and weigh each one of them 5 times. Make sure that you tare the scale before each one, and let it get to the final reading it's going to get, and then write it down. And then we're going to take the average of that. That's a good way to spell average. We're going to take the average of that. I think it's ABG there. Take the average of each reading for each cup, and then we're going to subtract the individual measurements from the average. That's going to tell us what the deviation from the average is for each single measurement. And then we're going to add all those together and determine what our average deviation is. That tells us basically what the uncertainty of the measurement with the balance is. And it should be pretty small. I mean, we should be shooting for something like, 0.01, 0.02 grams, like a really small amount. We should have pretty good accuracy with these scales. So, as long as you're not doing it in a windstorm or something like that, or blowing on it or whatever. Make sure that it's flat. If it's at any kind of an angle, it's going to screw up your measurements. So that's really important. So the next thing is then looking at the 4 different pieces of glassware. So we're going to put 7 mils. Oops. Let me go back. We're going to put 7 mils in the graduated cylinder, in the 10 mil graduated cylinder. We're going to put 24 mils in the 50 mil graduated cylinder. And then we're going to take our little 25 mil flask and put 17 mils in that. And then probably the most frustrating thing, we're going to try and put 35 mils into a 250 mil beaker that does not have any numbers until you get to 50. So that one's going to be tricky, because what we're going to do is we're going to try and determine what our uncertainty is. We're going to get the high and the low intervals, and they're going to be different for each one. For instance, right on the 50 mil, it will tell you, you can't really read it here, but if you read the top of it, it says 50 colon 1.0. So the 50 means it's a 50 mil cylinder. The 1.0 means there's a mark for every 1 mil. So that's going to define what your high and low intervals are. So for 24, if you get it like right around 24, your low interval is going to be 24 and your high interval is going to be 25, because that's basically as good as you can get with this. It's going to be right in between. What the intervals are written right on the instrument. Here on the 10 mil, it says 10 colon 0.2. Now what that means is the smallest measurements you can do on this one are 0.2 mils. So there's 5 ticks in between each mil, not 10. There's only 5. So our high and low intervals there will be different by 0.2 mils, not 0.1, like in the example given a little bit earlier. Then we're going to measure the mass of the water in each one. So you're going to need the mass of each one of these while empty, and then the mass of each one of them with the water in it, and then just subtract to figure out what the mass of the water is. Once you have the mass of the water, so here's where we put down our determination for the lab balance. All 5 masses there, all 5 for number 2. Give what the deviation from the average is, always positive number. And then we want the average deviation for 1 and 2. They should be pretty much the same. I'd be very surprised if you get 2 different deviations, unless you use 2 completely different cups. There we go. Yeah, right. So for the glassware, here's where we put the empty. Yeah. Here's where we put the empty masses. God, give me a break. I just love technology. Here we go. So here's where we put the mass of the empty glassware. And then write in what you estimate the volume of water is going to be. The high interval, the low interval, the measured uncertainty based on the formula you saw before, the mass with the water, and then the mass of the water. And then finally, for table 3, we're going to figure out what the volumes are. Using the density. So here's where you need the temperature. So you're going to, So current water temperature, we're going to assume it's the same all the way through. That's why I sort of recommend you don't use cold water and you don't use hot water, because the cold water is going to warm up. And so it'll be a different temperature for every reading. And the hot water is going to cool down. And so it'll be a different temperature for each reading. So use room temperature water. Then we're going to find, there's a table right in the directions that tell you what the density of the water is. And then that will help you calculate the actual volume of water in each one of the four. Okay. Here are the densities. So to use this, we just measure the temperature in the room. Let's say it's 20.5 degrees C. So we would go to 20, and then I would go across 0.1, 0.2, 0.3, 0.4. There it is, 20.5. So the density of my water, 20.5, is 0.9981. So you can see there's not a huge difference in density, right, in between 18 degrees and 28 degrees, but enough that it's going to affect your readings. At 18 degrees, the density is 0.998, and at 27.9 degrees, it's 0.996. That doesn't sound like a big difference, but it will affect the accuracy of your reading. And anything we can do, this is one of the ways, anything we can do to reduce the error in our measurements and reduce the error in our experimental design, we should do. This is one of them. So basically, we're taking into consideration what the actual density of water is, rather than just assuming it's 1 gram per mil. That's a good assumption, but you can see it is an assumption because it's not as precise as it could be. It's usually precise enough most of the time, but sometimes it's not precise enough when we want to get very, very accurate numbers. Okay. So any questions about that before we get started? I keep forgetting it's the quiet group. So quiet. All right, so you all know what you're going to do. Excellent. All right, so I'm going to give everyone 5 minutes to get all their stuff together, and then cameras on, and we will get started. Okay. All right, I'll see you in 5. Okay, everyone, get all your stuff together. Cameras on for those of you who can. There's everybody. All right, so yeah, so just to make sure you get the temperature of the water. That's going to be really important. And then make a note of what your high and low intervals are going to be. So it's going to be fairly easy for the 10 mil because it says right on it what the intervals are. And same with the 50 mil. It says what they are. But here on the 25 mil flask, you can see there's only two things that are written on it, 12.5 and 25. So that's basically going to be your intervals. So you can see that the uncertainty associated with that measurement is going to be pretty high. And then for the 250 mil, you're sort of on your own to try and figure out what your intervals are, because you can see that the lowest measurement is 50. And you're asked to do 35. But you have an advantage with this that you wouldn't have with this, because this is a conical shape, which makes trying to figure out what the interval is difficult. This is the same shape all the way up and down. So you know that these intervals are 10 mils. So you can do a fairly good job estimating where 35 is going to be. You could even mark on it with a marker or wax pencil or something, and put the intervals on it yourself. That will help your measurement be more accurate. But I'll leave it up to you to try and figure out what your high and low intervals are going to be when they're not even indicated here. I think your high and low intervals are going to be better than 0 and 50, right? Because I think you'll be able to do a much better job at estimating where 35 is as being somewhere between 0 and 50. I think you'll do a better job than that. Now, someone last night asked me, since you want to put 17 in here, can I just measure 10 plus 7 in the cylinder and then put it in there? That defeats the purpose of the experiment. We want to compare this as a measuring device to this as a measuring device. Okay. And one other thing that came up, if you look at the writing on the top of both of the large and the small graduated cylinders, right below where it tells you what the volume is and what the intervals are, it says TC/TD 20 degrees C. Anyone know what those mean, the TD and the TC? But you may have come across it in the hospital or something. If I tell you one, maybe you'll be able to tell me the other. So the TC means to contain. So basically this is guaranteed to contain 10 mils plus or minus 0.2. What do you think the TD means? Because there's two things that we want this to do. We want it to contain a volume, and then what do we want to do with it generally? What do you think? What do you normally do with this when you, let's say, normally in a typical experiment, it says get 10 mils of water. So you measure your 10 mils of water, and then what would you do with it?
Dispose.
Ooh, you're really close.
I mean, dispense.
Yeah. It actually means deliver, but yeah, exactly. It means to deliver or dispense, because this does two things, right? It not only contains something, it also, we needed to dispense it too. Whereas with this, we don't use it to deliver anything. We don't use this for measurement at all. So you won't see that written on there.
For the flask, is the low interval 12.5 and the highest 25?
That's right.
Okay.
That's right. Because what you're measuring a volume in between those two.
Gotcha.
And those are the only intervals on it. So yeah, so obviously the uncertainty for that one's going to be much higher than for anything else.
And then for the beaker, it's the low is 35 and the high is 50, correct? Intervals?
No, that one's going to be a little trickier because there's no intervals below 50. And so, I mean, what I would probably do is measure the distances between the intervals here and then just extend them down to 0.
Kind of like estimating, essentially.
Exactly.
Gotcha.
And so it may be Well, I don't know. It's basically, it's up to you. It's how you approach that particular problem. Everyone's given sort of a little bit of leeway on that one. If you just want to do it by eye, obviously your upper and lower bounds are going to be a lot greater than if you actually, try to extend this down to the bottom with lines and everything else. But it's totally your call, however you want to handle it.
Got you. Thank you, Professor.
No problem.
To measure 35 ml,
Right.
but the measurement starts beyond
Right.
40.
Didn't start till 50, right?
Yeah.
Yeah. So there's a number of different ways to approach this. Since this is a regular shape, basically it's the same width all the way down, you would probably be good to estimate that the 10 mil intervals are going to be the same all the way to the
All the
bottom,
way down.
right? It's a pretty good. So you can either
Plus minus.
mark
10.
them right on it yourself or estimate it. So basically that part of it is sort of up to you to estimate what you think the high and low intervals are. I mean, what probably wouldn't be the good thing to do is say that the low interval is 0 and the high interval is 50, because a measurement of 35 plus or minus 50 doesn't really, that's not really much of a measurement, right?
Yeah.
So yeah, so I don't know, I would think about, maybe marking some intervals on it and doing that. But it's up to your own judgment for that one.
Same thing with this one. We can also mark.
On this one,
because it's not.
on this one, the intervals are actually written on it.
Yeah, just the 12.5 to 25.
Yeah, that's it.
Oh, okay.
But because this is a conical shape, it's really hard to know where midway is in between there, because it's not going to be in the middle, is it?
Yeah.
Because it gets smaller. So the midway point is going to be closer to 12.5 than 25, which is why this is such a crappy measuring device. And we don't use it for that.
Okay.
But you can clearly use those two intervals for the flask. For the beaker, you kind of
estimate just.
Yep.
Okay. Thank you, Professor.
Yeah, don't feel bad when your 35 is way off, because that's kind of the point. Hopefully you get the 7 and the 30 and the 24 and the 50. You should be able to get those pretty close.